Hey, AP Physics students, welcome to the floor of room 117. So the podcast is all done. I filmed it all. You're about to watch it. As I'm watching through it, this sound of the spring being released is kind of loud. I wouldn't watch this video with headphones. I've been complained at before that sometimes the sound can be kind of piercing. I would watch it through speakers and don't have it up too loud until you know how loud that clicking is going to sound. You can always go back and rewind it if you didn't understand something totally. Watch the whole thing, make your data table, we'll post the CER questions on Emoto. That's all I got. Have a good weekend. Hello. So what you're going to be doing for the lab, the data we're going to be giving you, is pulling that down a certain amount. We flip that, the marble flies out, goes through this photo gate, give me a certain time. I'm going to give you the compression, so the X for the spring, and the time in this photo gate. I'm just going to tell you the numbers. You got to write them down on your own. I'm not going to fill in the data table for you like I did with weight versus mass, or like Mr. Ayers did, whoever. So we're going to have 5 different trials for notch 1, notch 2, notch 3, notch 4, and notch 5. Now, as I'm filming this, I'm realizing that we already filmed the data table part, but that's going to go after this part. So just write some stuff down off to the side, and then you're going to be making your data table in Excel anyway, so don't stress about it too much. Don't worry about the organization right now. Just make 5 lines, 1 for each notch, 1, 2, 3, 4, 5, and then you're going to have 5 X values and then 5 time values, and you'll fill in the rest later. So the physics of what's going on here. Right now, there's some energy stored in the spring. We'll talk next week about how the energy got there, but for right now, there's energy in that spring. If I go like that, all that energy comes out of the spring, and it goes into the marble in the form of kinetic energy. So now the marble's moving right there. Well, it's going to go up to a certain height, so now we have potential energy. So this first tick, we have a compression from right up here to right down here. The distance that we get for that is 6 centimeters. You will need to convert that to meters. And the time that we get is 0.051 seconds. Tick 2. We have a compression of 7.5 centimeters. Again, convert it to meters. And the time of 0.0038 seconds. I may have told you 0.051 seconds for the first trial. It was supposed to be 0.0051. Oops. For notch 3, we have a compression of 9 centimeters. Marble goes in. Time of 0.0031. Notch 4, 10.5 centimeters. And a time of 0.0025 seconds. And then finally, the big kahuna, notch 5, gives us a distance of 12 centimeters. You saw that one coming. And a time of, it's going to hit the ceiling, 0.0021 seconds. So again, the basic physics of what we have going on here. Energy is in the spring. Energy leaves the spring, goes into the marble. And then all of that energy is transferred up into potential energy. So in the next little bit, you're going to get what the data table should look like. You're going to make that in Excel. And you're going to put all of that in one big old fun Word document along with your CER answers, and you're going to turn that in through Turnitin. If you haven't already made a Turnitin account and joined the class, do it. See y'all in a bit. Hey y'all, as you saw in class today, we're going to be playing around with this a little bit, getting some data and thinking about the flow of energy that happens from right here to right there to up there. So we have this big data table laid out. We're not actually going to give you that much data in this today. All we're going to fill out is the distance compressed, which is going to be how long the spring goes down, how far the spring goes down from right here to wherever it is. We're going to measure that. That's the distance we compress. And then the time through the photo gate right there is however long it takes to go through that photo gate. The distance through the photo gate is the size of the marble, it's however big the marble is. That's not going to change for any of these. So all of these distances are going to be 0.014 meters, all the way down. That's what you're going to use to calculate the speed. So we can think about the speed right here, right when it leaves, and then think about the kinetic energy right here. Well, that kinetic energy is going to come from the elastic potential energy it had before the launch. We have a bunch of energy here. All of that energy turns into the kinetic energy. And then you can go through and fill in the rest of the data table, finding the spring constant at each of these different notches, how high the thing goes at each of these different spots, so on and so forth. In the next segment, we'll have, and we're going to film later today, we'll have the data points you need for the time right here, and then how far this is pulled down. One more number that you'll need will be the mass of the marble, which I'm just now realizing I haven't written up there. So down somewhere near the data table, when you make your data table on the computer, you're going to need to have a column for the mass of the marble. It's 0.004 kilograms. So I just use the word computer. You're going to be doing this data table on the computer. You're going to be making it in Excel, and then you're going to be turning it in with your CER questions in Turnitin. It's going to be pushed right in the middle of the Word document. If you don't know how to do that, ask one of us. We'll tell you how to put it in there. It's very easy. And then you're going to turn all of that in at once through Turnitin. Be right back. So basic physics that we have going on here, pretty straightforward. Energy turns into energy, turns into energy. What we're going to think about is how to actually do the math to get the various things that you need. Now, we know that this is always true. The total initial energy is equal to the total final energy. That's what conservation of energy actually means. The next step is to think about what possible energies can we have at any point in our problem. Well, we have kinetic stuff because it's moving. We have gravitational potential because it's going up and down. And then we have spring potential energy because there's a spring that's going to be squished or stretched or something. So we have K initial plus gravitational initial plus spring initial. I use I's for initial. Ayers is kids. That makes Mr. Ayers crazy, but live with it. We can also have those exact same things, but final instead. Now, the step that you're going to be doing when you go through and make your calculations, you need to think about what you're going to cross off. So, at the very, very beginning, the spring is squished. Where is the energy? Well, it's not moving, so we can cross that off. We're going to be able to cross that off anytime, no matter what. And then we get to that issue of the gravitational potential energy. Well, 0 for gravitational potential energy is wherever we want it to be. So if our setup down there is some amount of centimeters off the ground, let's say that that's our 0. Let's say that we're trying to find a height above where the marble is at the beginning, which means we always get to cross that off too. It doesn't matter where the marble starts, we care about how high it goes above that. The spring is always going to be compressed, so we always have that. Then that part right there kind of depends on which part you're doing. If you're trying to find the kinetic energy of the marble right when it leaves, right after the spring goes, if you're trying to find the kinetic energy right there, well, that's still right there at the beginning, and we said that there was no gravitational potential energy right there, so we can cross that off. Well, if it's right after the spring launches it, the spring is not compressed, so we can get rid of that. That means that we only have final kinetic energy. That's only for finding the final kinetic energy. If we're talking about the marble going up to the very top, well, now we're comparing the initial situation, which is the same, but now all of the energy is in gravitational potential energy. Remember that anytime something goes up to the top, right there, it stops. So that goes away for finding the height. That's obviously there because it's above the ground. And then the spring is no longer stretched or compressed or anything, so we get to get rid of that too. In addition to what you're going to be turning in through Turnitin, meaning the CER questions and the data table, you're going to be showing an example of how you got all of one row in your data table. You're going to turn this in to us the day the lab is due. It's not on Turnitin. You're going to need to work this process. Show us the math. Show us how you calculated the height. Show us how you calculated the spring constant. You've basically done these problems already in homework and in class. Here you're just doing them with actual real numbers, and you're finding some real spring constants. You're showing us how you do it. Then you're going to turn it into us and get a really, really good grade before the end of the 6 weeks. Y'all are going to have until the end of next week to do this. We're going to make this due on Friday, so make sure you get all of it done. You have the weekend to do it. If you have any questions, you can look back at this, or you can come in tutorials or ask during class. See y'all next week.